Hello everyone, welcome to Mayur Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is most stone removed with same row or column. Okay, so the problem statement goes like this: on a 2D plane, we will be placing n stones at some integer coordinate points. Okay, and each coordinate point may have at most one stone. Okay, so there will not be two stones in at a particular coordinate. So a stone can be removed, two or more stones will be not there, basically only zero or one stone can be there at a particular coordinate. And a stone can be removed if it shares same row or same column as another stone that has not been removed. Okay, given an array of stones of length n, you will where each entry in this stones array is the coordinate of that particular stone. Okay, and represents the location of the ith stone, as I already told you. And return the largest possible number of stones that you can remove, provided that you follow the following rules: that a stone can only be removed if either there are some stones in its row or in its column. Okay, only then it can be removed. Okay, so what I mean to say is, for example, this is a 2D plane. Okay, and there is a stone here, and there is another stone here. Okay, as you can see, for the column and the row of this particular red stone, there is no stone present, no stone present in this column, and no stone present in this row. So you cannot remove this. Had it been the case that this blue one was present somewhere, let's say here, then you could have removed the red one, because although there are no stones in its column, which it is in, but there is a stone in its row. So that's why you can remove this. Okay, so that's what the problem statement is saying. Provided you are following this constraint, you have to tell how many maximum number of stones you can remove. Okay, return the largest possible number of stones that can be removed. So before thinking of an approach, let's have a quick look at the constraints also. So see, according to the constraints, the length of this stones array that will be given to you will be of order 1000, and each entry in it will be ranging from 0 to 10 raised to power 4. Okay, the coordinates I am talking about, the coordinates will range from 0 to 10 raised to power 4, both inclusive. Okay, and it is mentioned that no two stones are at the same coordinate point, as it was already mentioned that there will be at least at most one stone at each coordinate. Okay, so now let's think of an approach how we can solve this particular one. In order to solve it, what we can do is we have to make couple of observations. The first observation is, let's say we take the previous example only. So since there were two stones, okay, and you could have removed basically any of them. Okay, but not both. Why? Because you know once you remove this red stone and it's out of the picture, let's remove it. Okay, now let's say this is gone. The only stone remaining now is this blue one, and there is no stone in the column in which the blue one is, or the row in which the blue one is. Okay, you cannot remove any further. And had it been, let's say, three stones instead of two. Okay, so let's keep the red one intact and let's introduce one another stone. So let's say there is a yellow one here. Okay, so let's say I first removed the red one. Okay, and then blue one can also be removed since it was having one stone in its column. Okay, So I was having a choice, either I can remove the yellow one or blue one. So let's say I decided to remove the blue one. Okay, and the blue one is gone. So the only stone remaining in the whole grid, although let's say there are some other stones also. Okay, just to make things little more observable, let's consider there are some other stones also, but the yellow one is not having any stone in its row or column, so that's why it will remain as it is. Okay, so in a way we can say that these three stones that we took already, the blue, yellow and the red one, were forming a kind of group like thing. Okay, so they were forming a group like structure. Okay, so they were present in a group, and now you should be understanding that there can be many groups which are connected with each other by sharing the rows and columns. Okay, so let's say there is another white stone. Okay, and this white stone is again, let's say, sharing row with this green stone. So you see, this particular group is one group. Okay, the one with white dots, and the one with blue dots is another group. Okay, but these two groups are not related with each other, since they are not sharing any rows or columns. Okay, so you see how many number of stones you can remove in the blue group. In the blue group you can remove basically two stones out of three, because for the third one there will be no stone left with its in its current row or column, and I by mistake have, took this green one in the same uh, row with the yellow one. Instead of in the taking it in the same row, let's move it to a different row. Okay, in order to make the example the correct one, so let's move it here so that it is not sharing any row or column with the previous group. Okay, so I hope now it's clear to you that blue group, out of three, only two stones, and white group, only one stone out of two. Okay, so you see one stone will always be remaining in a group, and we can somehow, by the help of these columns and groups, form groups. Okay, and these groups are disjoint groups. Okay, so disjoint groups, blue and the white one, are disjoint because they are not sharing any rows or columns. Okay, so disjoint groups, both of these. Okay, so since let's say, as we can see on the grid right now, there are five stones. Okay, and out of five stones, those five stones can be converted into two disjoint groups. Okay, so since two disjoint groups, five stones, and each disjoint group will have one remaining stone. So if you subtract the number of stones with the number of disjoint groups, then you will get the number of stones, maximum number of stones that you can remove from the current stones present on the grid. Okay, so the formula becomes number of stones, okay, minus number of disjoint groups, or you can say number of connected components. So these components, groups are called components. Here I am referring to them as components. So number of connected groups or number of connected components. Okay, so this is what the problem statement of finding the maximum number of stones boils down to. Okay, you have to find, okay, number of stones is already given to you, that is the size of the your stones array, and number of connected components, for that you should be finding out the number of groups that you can make basically. Okay, so you should figure out a way to find the number of connected components. Okay, the whole problem boils down to finding the number of connected components. So let's see how we can do that. For that, a prerequisite will be that you should be knowing about the concept of union find data structure. Okay, or disjoint union find. Okay, basically the name is disjoint set, okay, of the data structure, and the algorithm that we will be using is union find. Okay, so this is a data structure. Let me light it clearly here. Disjoint set. So as the name suggests also, this kind of data structure, there will be sets which will be disjoint from each other, not sharing any common connection. Okay, and we will be using union find algorithm, okay, in it. So if you are not familiar with it, then I would say that I will be providing link of couple of articles on what this data structure is, disjoint set, and how to implement it. Basically there are a couple of implementations, basic implementation, and then uh, optimization on top of that. But I will also give you a brief overview how this thing works. So I will be explaining you along with the code, okay, so that the problem solution does not becomes very lengthy. Otherwise, in order to explain it, separate video would be required. So that's why you should be definitely checking the article links that I will be giving you on this particular data structure. And then, assuming that you have now familiarized yourself with this data structure, now let's see how we can use this to find the number of connected components. Okay, so let's see how we have implemented this approach. And for that, I am taking the code to the board so that it will help me to explain you, and it will also make the solution video concise. Okay, so I know it's a little bit lengthy, but the lengthy part is just for implementing this union find data structure. Okay, otherwise it's just you can say this much only. The function is this much, but this is the data structure that we have implemented. So we will be talking about that. So first observation was that there will be different groups, and the number of stones you can remove will be this much. Okay, now the problem was to find the number of connected components. So see, each stone basically connects its row and columns. Each stone will be present in some row and some column. In a way, you can say that if this stone is present here, okay, so this one is the row of this stone, okay, row, and this one is the column of this column. So you can see that stone is just like a connecting point which brings together its row and column. Okay, so you can say that a row can have, basically let's say this is R1. This R1 row can have stones at different columns. Okay, let's say we are talking about this row only. This row can have stones at the this particular column. Let's say C1, C2, C3, R1, R2, R3. Okay, since R2 is having stones at C2 and C3. Okay, so let's say this was R2, and it was having stones at C2 and C3. Okay, now see, if we consider column, then this column can also have stones at different rows. Okay, let's say C3 is having a stone at R3 also. Okay, so you see, R3 is connected with C2. Okay, so I hope you are able to observe, not C2 exact, it will be with C3. Okay, since the stone was here in the C3 column, so C, C3 is also sharing a stone with R3. Okay, so see, there can be different configurations like this. Okay, and if you take them as a single group, you know, by combining the groups, rows and columns this way. Okay, considering them as separate identifiers. Okay, and grouping them together, this like this, you can group stones together. Okay, in a way the stones just came together as a single group. Okay, that's why what we will be doing here is, for each stone, since it was combining its row and column. Okay, so in order to group these stones efficiently into different disjoint groups. Okay, we what we would be doing is, firstly I will be explaining you the union find, uh this whole data structure in a little bit of time. Firstly I would like to discuss that how this union operation is working. Okay, or making the groups is working, what is the logic behind making the groups. So you are taking the row and the column at which a stone is present, and since stone is in a way connecting its row and column, so you will make a group of these two, just like we did here. Okay, so for example, we just did it with R2 and C2. Okay, this was one stone's coordinate. Okay, this blue one's coordinate, R2 and C2. So you will do like this. Okay, and when you will keep doing like this, grouping rows and columns like this, you will be having the stones which are sharing either a row or a column together in a single group. Okay, so that's why we are using this kind of logic. Okay, union is just that we are forming a group. Okay, and then uh, each group will be selecting a group leader. Okay, so group leader, in a way you can consider it like this. Let's say there are three components or three stones in a group, and they will say that, okay, we will select a representative of ourselves, and that representative will uniquely identify our group. Okay, just like it happens in elections of a particular region. Okay, let's say this is region 1 or group 1. Okay, so it selects its representative to represent the whole group. Okay, if you, let's say, let's give them names. Okay, A, B, C. Okay, and let's say the representative is right now A. Okay, let's uh, write R here, or REP, representative. So if you ask A, who is the representative of your group, A will answer, my representative of my group is A, myself. If you ask B, who is the representative of your group, B will say it's A. If you ask C, who is the representative of your group, C will answer it's A. Okay, similarly there can be another group. Let's say this yellow one, D, E, F. Okay, there are three stones here also, and let's say we make the representative D. Okay, D is the representative, so D is the representative if you ask any of these. Okay, so in a way the number of distinct components will be equal to the number of distinct representatives. Okay, we can call these representatives as roots also. Okay, so here we have called them roots. So number of unique roots will be equal to the number of different components. Okay, and this is what essentially this data structure disjoint set also does. Okay, so first of all, as we talked about, we will be uh, making the rows and columns into a single group in order to group the stones efficiently, just like we did in this particular slide. See here we are doing that. Okay, so it will help you to group your stones effectively. Then once you form the groups and you are having group representatives, those group represented the number of distinct group representatives or the number of distinct roots will be the number of connected components. So see here only two distinct representatives were there, and those were D and A, and so the size was 2, and in all let's say there are 6 stones, so 6 minus 2 will be 4. Okay, maximum 4 stones you can remove. You should be keeping at least one stone remaining in this group and one stone remaining in this group. Okay, so this is the whole logic. And if you want to have a quick discussion on this union find also, it also does the same thing. See, this find operation is the kind of auxiliary operation. It is just to find the group leader, okay, or find the group representative, okay, or you can say head or leader, whatever you may want to call it. Okay, so initially what we will be doing is basically we have used the optimized version, but I will be trying to make you understand the basic one. Since initially each of the stones, let's say 1, 2 and 3, each will be the group leader of itself. So we will be initially having groups of 1. Okay, so all will be their group leader and the group size will be 1 for all. Okay, so this rank is I will tell you in a bit what rank is also. So initially 1 is the group leader of itself, 2 is the group leader of itself, and 3 is the group leader of itself. Okay, and if you are see in this diagram also, if you ask A who is the group leader of your group, A will answer that I am the group leader of this group. So whatever the person is able to answer that I am the group leader, he or she will be the group leader. So initially groups will be of size 1 and everyone will be the group leader of their own group. Okay, then let's say you have to merge 1 and 2 nodes, 1 and 2 you have to merge, you have to do a union of them. Okay, so firstly you should be asking 1 and 2, tell me, tell us our group that what are your group leaders. Okay, so 1 and 2 will say that our group leaders are ourselves. Okay, so 1 is the group leader of itself and 2 is the group leader of itself. Okay, so initially rank is 1. So rank is, consider it like this, there are a bunch of gorillas. Okay, and they are fighting with each other. So initially everyone is having a fight count of or win count of 1. Okay, win count you can say of 1. This one is also having win count of 1. And let's say uh, let's give them colors. This is the blue one and this is the yellow one. Now let's say the yellow one defeats the blue one, so its win count will be increased. In a way this win count is just that only. Okay, in a fight how many wins it has got. Okay, basically initially we have set everyone's win count to 1. So the more the number of win counts, the likely will be the chances that this blue one will surrender to this one. Okay, and will become a part of this one, this group of this uh, yellow one's group. Okay, in which the yellow one will be the group leader. Okay, this is what we are doing in order to prevent a situation like this. See, you can see this as a kind of a tree like structure where the root is the group leader, and the childrens are just their followers, or you can say the non-leader persons in the group. Okay, we are wanting to keep this tree as much as flat as possible in order to reduce the basically the time complexity. You will find it more about in depth in the articles link that I have provided for this particular implementation and data structure, you can say. So in a way it is happening like that only. So if they are having the same group head, then it means that they are in the same group, then there is no point of proceeding any further. In if there are different group heads, then you will see who is having the higher rank. The higher is the rank, the more likely is the chances of that particular gorilla or the person, you can say, to remain the group head. Okay, and this is what the logic is. And if they are of same ranks, see, if the ranks are higher, the one with the lower rank will already surrender to the one with the higher rank. But if the ranks are higher, then there will be a fight, and the you can by default increase any of the contenders rank by saying that okay, this will emerge as the uh, group head. Okay, so we here we are just increasing the rank of that particular uh, you can say head that we have chosen by default. Okay, and parent is just like array that will be showing the group leader in a way. Okay, you can say parent or group leader. I have just used a analogy to make you understand. Okay, this is as close as I can get to make you understand this data structure. And apart from that, if you want to have an in-depth of understanding of it, then you should be definitely considering going over to those articles and reading more about it. Okay, and as far as the time complexities are being concerned, see, a loose upper bound of this union operation that we are using, or this find operation, basically union operation is also using this find operation internally. So we can say that for these couple of observation operations that we are using, find and the union above, internally union is also calling find. So a loose upper bound of this can be order of log of n. Okay, and if there are n calls being made, since let's say the size of this stones array is n, so the order of n calls are made. So in total the time complexity becomes order of n log of n. Okay, and this is just a loose upper bound. In reality it will not be that much, even to the, in terms of logarithm. You can consider it closely to linear time complexity, but if you want to take a loose upper bound, so we can take this much. Okay, this is just a loose upper bound. So loose upper bound is something like this: if someone is having a higher time complexity and some function is having a lower time complexity, we can consider it as a loose upper bound, or in a way you can say that a cover of the lower time complexity function. Okay, so even with this time complexity and the constraints that you are being given, the constraints were that the number of stones will be of order 1000. So our solution will anyways be getting accepted. Okay, it will, even if it was n square, then also it would have been accepted because it's 10 raised to power 3 only. So that's why. So this is the time complexity. And as far as the space complexity is being concerned, so what we are doing here is, I forgot to tell you the logic how we are adjusting x and y in the parents array. Okay, so we are doing a offset of the points were ranging from 1 to 10 raised to power 4. So that's why a offset of this much will be for the y coordinate. Okay, so that x and y coordinate do not overlap in this particular parents array. Okay, so that is how we are adjusting them, and this is the whole logic and approach. I hope you find it interesting and the analogy to be understandable. And if you are still having any kind of doubts or any queries in general, then you may ask them in the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSA skills, and keep solving more and more problems. And I will be seeing you in the next video. Thank you for watching.